Seats, they include the critical angle and the total internal reflection. What is critical angle? By definition, the critical angle is the angle of incidence at which the angle of refraction is 90 degrees when light passes from denser to less dense medium, that is, a glass prism to air or water to air, and so on and so forth. The incident angle at which the refracted ray lies along the interface, that is, at which the angle of refraction is 90 degrees. Right angle triangle is known as the critical angle. Diagram below illustrates the critical angle. The incident ray originates from within the medium of the pool of water or a swimming pool. You can see it growing and emanating. It meets the normal, and on the normal you can see it is refracted towards the surface of the pool of water, and hence we have a right angle in between y positive and x positive. So critical angle is equal to 90 degrees. Hence, the incident angle at which the refracted ray lies along the interface, that is, at which the angle of refraction is 90 degrees, is known as the critical angle, theta c. As critical angle, the triune components of the critical angle include the incident ray or incident angle, we have the refracted ray or the angle of refraction, and then we have the media, the less dense and the denser. Internal reflection, on the other hand, is the reflection of an incident ray of light at the interface between the medium of incidence and another medium of lower density, when the angle of incidence in the denser medium exceeds the critical angle. For glass example, the refractive index is constant, which is 1.5. When the angle of incidence exceeds 42 degrees, total internal reflection occurs. So total internal reflection, when the angle of incidence is increased beyond the critical angle, then the refracted ray disappears and a strong reflected ray is obtained. At this stage, the incident ray is said to be total internal reflection. Is illustrated with the diagram as seen on the screen. It is a reflection of an incident ray of light at the interface between the medium of incidence, which is the pool of water, and another medium of lower density, which is air, when the angle of incidence in the denser medium, which is the pool of water, exceeds the critical angle, which is the interface representing x. For glass of refractive index 1.5, when the angle of incidence exceeds 42 degrees, total internal reflections occur, and some conditions must be met. The first, light must be traveling from an optically more dense medium to an optically less dense medium, and then the angle of incidence in the denser medium must exceed the critical angle so that total internal reflection can occur. The two angles in between the normal are equal, provided the water surface is not ruffled. A fish underwater or a swimmer moving on his back underwater has its field of view widened. It can see everything above the water surface and objects in the water. From the diagram, you can see that the fish can see every object within the angle of 98 degrees. The finger is pointing at the objects above the water surface. You see the image of whatever object is displayed in air at the point where the finger is located. Hence, we can be able to calculate mathematically the refractive index of air to water as the rays of light travels from air to water is 4/3, is a constant value, so that the angle of incidence is equal to 90 degrees. The angle of refraction is equal to r. Remember, by substitution, 4 divided by 3 is equal to sine 90 divided by sine r. 4/3 is equal to 1 over sine r, because sine 90 is 1. Therefore, sine r is equal to 3/4, and then g, which equals 0.75.
The sine inverse of 0.75 is equal to 49 degrees approximately. 49 degrees multiplied by 2 will give you 98 degrees. If you relate this to percentage, you see that it's almost 100%. If fishes can see at this level, how far do you think God can see? The triune components of total internal reflection, we have the angle of incidence, we have the angle of reflection, then we have our media, which is water and air. But most importantly, under total internal reflection, only one media is projected because the ray of light is reflected within a single media. What are the natural applications of total internal reflection? They are categorized into two. The first, we have nature. The second, we have artificial application. For the first, in nature, we have mirage. It is an optical illusion caused by atmospheric conditions, especially the appearance of a sheet of water in a desert or on a hot road caused by the refraction of light from the sky by heated air. Can be optical illusion, hallucination, or it is an optical illusion caused by total internal reflection of light at the separation of two layers of air of different density. The media is air and air, but the upper side has a lesser density than that of the lower end of air towards the surface. Now, or it is an optical illusion caused by total internal reflection of light at the separation of two layers of air of different density, making a traveler along a tarmac road on a hot day to seem to see pools of water ahead, which disappears as he approaches. So, the air around the tarmac road seems to be warmer or hotter than the air rightly above the tarmac road. Because of that, total internal reflection occurs, and then the image of the sky is casted on the road, and a driver from afar, probably from a hilly road, will see a slopy road with an image of the sky being casted as water. The rays from a patch of the sky, a traveler, or rays from a patch of the sky, let's say medium A, travel from cold air layers of higher densities to warm or hotter air layers of lower densities. The rays bend gradually from the incident directions as they travel from layers of higher densities to those of lower densities. The incident angle is increased in the process such that a certain interface between a denser layer and a less dense layer, the critical angle is exceeded and total internal reflection occurs. The ray is reflected to the eye of the observer, and then it appears to be as if an image of the sky is casted upon the road. The image of the patch of the sky appears to the observer as a pool of water. Number 2 application, field of view of a fish underwater. Provided the water surface is not ruffled, a fish underwater or a swimmer moving on his back underwater has its field of view widened. It can see everything above the water surface and objects in the water. So these are the two applications of total internal reflection. Artificial applications. We have number 1, optical fibers. You've heard of optical fibers? They are very thin, flexible glass tube through which light signals can travel over a long distance by a means of total internal reflection within the tube itself. Its diameter is roughly the same as that of a human hair. It consists of a central glass core surrounded by a glass coating of lesser density, which is lesser refractive index than the core. Total internal reflection then occurs repeatedly at the interface between the core and the coating until the light signals emerges at the other end of the fiber optic cable. Optical fibers has the following uses or applications. They are used in telecommunication to transmit signals over long distances at higher bandwidths, which is database, than metal wires, which were previously used. They are used for illumination and can be used to carry images because they are wrapped in bundles. They can be specifically designed to be used as sensors in fiber lasers. Advantages of optical fibers over metal wires: higher or broadband width. They are not affected by nearby electromagnetic radiation. They are electrically non-conductive, and so it does not pick signals like an antenna. The material cost is less compared to copper cable, and hence are lesser attractive to thieves.
Connect to our social media handles at Physics Bible, the Triune Physics, for latest update. Thanks for joining us. Stay equipped, stay liquid.